Hello everyone, and welcome to today's presentation. I'm excited to share with you a fascinating proof that square root 2 is irrational. The title of our talk is Proof that Square Root 2 is Irrational Detailed Step by Step, and we'll be focusing on a specific method called the parity contradiction method. Over the next few slides, we'll walk through the logic step by step to understand why square root 2 cannot be expressed as a simple fraction. Let's get started. All right, so let's dive into step 1 of our proof. Here, we're clearly stating our goal. We want to prove that the square root of 2, which we write as square root 2, is not a rational number. Now, why is this important? Well, establishing whether a number is rational or irrational is fundamental in understanding the nature of real numbers. By setting this goal, we're focusing on showing that square root 2 cannot be expressed as a simple fraction, meaning it cannot be written as a ratio of two integers. This step is crucial because it frames the entire proof process. So, in essence, our starting point is to demonstrate that square root 2 is irrational, and that's what we're here to do. This statement of goal guides the entire logical journey we're about to undertake. Now, let's move on to step 2. Here, we're going to recall the definition of a rational number. A rational number is any number that can be written as a fraction, specifically as p divided by q. The key here is that both p and q are integers, meaning whole numbers, and q cannot be 0 because division by 0 is undefined. This simple definition is important because it helps us identify which numbers are rational and distinguishes them from irrational numbers. Understanding this concept is fundamental as we explore different types of numbers and their properties throughout this presentation. All right, so for step 3, we're going to approach this using a proof by contradiction. The idea here is to assume the opposite of what we want to prove, just to see if that leads us anywhere interesting. Specifically, we're going to assume that the square root of 2 is actually rational. Now, saying that means we can express square root 2 as a fraction p over q, where p and q are integers. And of course, q can't be 0 because division by 0 isn't defined. This assumption sets the stage for us to explore whether this rational representation can hold true, or if it will lead to a contradiction. This is a common technique in proofs. By assuming the opposite, we can often uncover inconsistencies that help us prove our original statement. So, let's keep this assumption in mind as we move forward. All right, now we're at step 4, lowest terms. Here, the key idea is that we want to choose p and q so that they don't have any common factors other than 1. In other words, their greatest common divisor, or GCD, should be 1. This means that p and q are as simplified as possible, with no common divisors that could be factored out. This step is really important because it ensures that the fraction is in its simplest form, which makes it easier to work with and understand. Remember, reducing fractions to lowest terms is a fundamental part of working with rational numbers and simplifies the overall process of analyzing these relationships. So, always look for the greatest common divisor and divide both numerator and denominator by it to get the lowest terms. All right, now that we've established our initial equation, let's move on to step 5, squaring both sides. What this means is we take both sides of the equation and raise them to the power of 2. So on the left, we have the square of the square root of 2, which is written as square root 2, 2. On the right, we have p/q2. When we square the square root of 2, it simplifies nicely because the square and the square root are inverse operations, so we're left with just 2. On the other side, squaring p over q means we square both numerator and denominator separately, giving us p2 over q2. So the key point here is that squaring both sides helps us eliminate the radical on the left, making our equation easier to work with. This step is crucial because it allows us to move forward with our proof by connecting the properties of squares and roots. Remember, this step is part of the overall process to show whether square root 2 can be expressed as a ratio of integers, which is what we're exploring in this proof. All right, now we're at step 6, which is all about eliminating the denominator. To do this, we multiply both sides of the equation by q squared. By doing this, the equation transforms from a fraction to a whole number, making it easier to work with. So, multiplying both sides by q2, we get 2q2 equals p squared. This step is crucial because it helps us clear the fraction and set us up for the next steps in the proof. Remember, the key idea here is to manipulate the equation to have whole numbers on both sides, which simplifies the analysis moving forward. All right, let's move on to step 7, which is about the evenness of P2. Now, from our previous steps, we know that P2 equals 2 times Q2. Since there's a 2 multiplied by Q2, it means that P2 must be an even number. And why is that? Because any number that's a multiple of 2 is, of course, even. So the key point here is that P2 being equal to 2Q2 directly tells us that P2 is even. This is an important step because it helps us understand the properties of P and Q in our proof. Remember, this idea of evenness is central to the overall argument we're building, especially when we're trying to reach a contradiction or prove something about the nature of P and Q. So, in essence, recognizing that P2 is even sets the stage for the next steps in our reasoning. All right, let's take a closer look at step 8. Here, we're focusing on the evenness of P. The key idea is that if P squared is even, then P itself must also be even. Now, why is that? Well, think about the properties of odd and even numbers. The critical point is that the square of an odd number is always odd. So if P squared is even, it can't be the square of an odd number. That means P has to be even. This step helps us understand the relationship between a number and its square, which is essential for our overall discussion about number properties and proofs. All right, let's move on to step 9. In this step, we're going to express P as 2k, which means writing P as twice some integer k, so we'll say P equals 2k, where k is just an integer, could be any whole number, positive or negative. This is an important step because it helps us analyze whether P is even or odd, and that plays a big role in our overall proof or problem-solving process. By representing P this way, we can easily explore its properties and see how it relates to other elements in our problem. Remember, the key idea here is that expressing P as 2k simplifies our work and connects to the broader theme of understanding the structure of numbers, especially in contexts like divisibility or parity. All right, now let's move on to step 10. Here, we're making a substitution, P equals 2k. This is a common technique to simplify the problem and see the relationships more clearly. So we take our original equation, 2q squared equals P squared, and replace P with 2k. That gives us 2q squared equals 2k squared. When we expand that, it becomes 2q squared equals 4k squared. This step is crucial because it helps us express everything in terms of k, which can make analyzing the properties of the numbers involved much easier. It's a key move toward understanding the nature of these squares and how they relate to each other within the broader proof. All right, now we're at step 11, which is all about simplifying the equation. The key idea here is to divide both sides of the equation by 2. When we do that, the original equation q squared equals 2k squared becomes much cleaner. Q squared equals 2 times k squared. This step is crucial because it allows us to analyze the properties of q and k more easily. By simplifying the equation, we're setting the stage for the next logical steps in our proof. It's a simple move, but it has a big impact on how we understand the relationship between q and k. This step also illustrates the power of algebraic manipulation in revealing deeper truths, something that's central to the overall theme of proving irrationality. All right, let's look at step 12, which focuses on the evenness of Q2. Now, if Q2 is even, what does that tell us about Q itself? Well, in mathematics, if a square number is even, then the original number must also be even. That's because the square of an odd number is odd, and the square of an even number is even. So in this case, since Q2 is even, we can conclude that Q must be even as well. This is a key point because it helps us understand the properties of the variables involved and how they relate to each other within the overall problem. Recognizing this connection is crucial for progressing through the proof or solution we're working on. It's a fundamental step that simplifies our next moves significantly, especially when dealing with divisibility or factorization. So always remember, when you see an even square, the original number is even. Now let's move on to step 13. Here, we're considering the case where both P and Q are even. This is a crucial point because it tells us that P and Q share a common factor of 2. In other words, both numbers are divisible by 2. This shared factor is significant because it impacts the properties of P and Q, especially when we're exploring their relationship and potential contradictions in our proof. Recognizing that both are even simplifies certain parts of our argument and helps us understand the structure of these numbers more clearly. This step connects directly to our overall theme of examining the nature of these numbers and understanding how their divisibility properties influence the larger proof or concept we're working through. All right, so here we're at step 14, which is all about examining a contradiction. Previously, we assumed that P over Q was in its lowest terms, meaning that the greatest common divisor, or GCD, of P and Q was 1. That's a key point because it tells us that P and Q share no common factors except 1. But now, here, where the contradiction comes in, both P and Q are even numbers. And if both are even, that means they're divisible by 2, which in turn means their GCD is at least 2. This is a crucial realization because it directly contradicts our initial assumption that GCD was 1. So, by showing both P and Q are even, we're essentially proving that our original assumption can't hold, and that's what leads us to the conclusion about the irrationality of the number we're analyzing. It's a powerful step because it reveals the inconsistency in assuming the number was rational, and that's the core idea behind this proof. Now, for step 15, the conclusion. Here, we see that our initial assumption that square root 2 is rational actually turns out to be false. This is a crucial point because it shows that our earlier hypothesis doesn't hold up under scrutiny. As a result, we can confidently state that square root 2 is irrational. This conclusion is significant because it reinforces the overall theme of our presentation, understanding the nature of irrational numbers and how they differ from rational ones. Remember, this proof helps us appreciate the beauty of mathematical logic and the importance of rigor in our reasoning.